Hi class, this is lessons 5.2 and 5.8, graphing polynomials. This frame is about relating zeros. Intercepts. And solutions. So that's the first column. Also, it's about using your calculator, your graphing calculator, using also your calculator, and substituting. So we got a few different things here. So let's look at the first column. First column's zeros, intercepts, and solutions. They're all equal to each other. They really mean about the same thing. So let's look at how they are related. So our first one here is given that f of x equals this function right here. What are the solutions? Well, we've talked about this a few times. The solutions are the things that would make each of these 0. So 2 would make this one 0, so x equals 2 is a solution. The next one, negative 3i would make it 0, so x equals negative 3i is a solution. And the final thing, positive 3i, would make that last one 0, so x equals 3i is also a solution. So there are 3 zeros there. And the zeros are the solutions. The next one here, given that f of x equals this, how many zeros are there and what are they? Well, see, I have this squared. So negative 1 would make this 0, but it happens twice. So I have 1, 2, 3, 4 zeros. Okay, 4 zeros. And their x equals negative 1, x equals positive 1, and x equals 3. Now I only wrote 3 numbers because this first one happens 2 times. And that's why I know there's 4 of them. This third problem, if x equals negative 4 and x equals 2 are solutions, what are the corresponding factors? So think of what it looks like when I put something in factored form. I need to know what could I put these into, what factors would these go into, that those would make it 0. So that would be x plus 4, and negative 4 would make that one 0. Then my other would be x minus 2, because positive 2 would make that one 0. Okay, so what we need to remember is if the graph touches the x-axis at a 0, so if it just touches, then my degree at that spot equals 2. It happens twice. If a graph crosses the x-axis at a 0, then the degree of that number is just 1. It happens 1 time. All right, let's look next at our local maximums and minimums in 0 on our graphing calculator. I'm going to give you the rules that you need to follow. You should write these down, and then tomorrow in class we'll actually use them in your graphing calculator so you'll have the chance to make sure that you can do this correctly. You can try it on your own tonight, but we'll definitely have the chance to ask questions about this, but at least you'll have it written, directions written down first. So we're going to find the max or minimum on our calculator. The first thing we're going to do is input our function. And y equals. I'll put a box around it because that's a button on our calculator. Then we're going to hit second. Again, that's a button, and trace. And that's another button. The second thing you're going to do here is calculate the minimum or maximum. So we want to calculate and pick which one you're going to calculate and pick that value. If you want a minimum, hit the min button, or the number that chooses minimum. Or if you want the maximum value, pick the number that chooses the maximum. So number 3, a little blinking thing will occur on your graph, and you want to move that left of your max or min, whichever one you're finding, and then hit enter. And a little arrow will occur up above. The fourth thing you want to do is then go right of your max or your min, and then you're going to enter twice. That second enter actually does the calculating. And then the fifth thing, finally, you'll get your point. And that'll be listed down at the bottom of your screen. So that's how we find the max and the minimum. Make sure you have those directions written down. You can try it on your calculator and see if you can get the bottom ones right, but we will talk about it in class. So to find our zeros on the calculator, the first thing you have to do is, again, input your function into y equals. Okay, and then we're going to still do the same thing. So input into y equals, that looked like a funny sign there, and hit second and trace. So we're doing the same first step here. Okay, we're going to go to the exact same spot. Second thing we're going to do, we want to calculate. And here we want to calculate 0. So we're going to pick the number that gives us 0. The third thing we're going to do is the same as really the third and the fourth step. So I'm just going to put it into one step. We're going to go to the left and then to the right. We're going to do the third and fourth steps of 0. And we're going to hit enter between. So really that's the same as the third and fourth steps up above, and that will give us our 0. So they're really similar steps to find your max and min and finding your zeros. I'm going to give you the answers to these next ones. These are ones I actually did go through and do on my graphing calculator. And so you can follow these steps and try and get these values on your graphing calculator. But we will go through some in class as well tomorrow. It'd be a good idea, though, if you try it on your own and see what you can get right and what you're going to struggle with. So my intercepts are negative 1.730, 1, 0, and 1.730. If you put it into your graphing calculator, it crosses the x-axis 3 times, so we need to find all of them. Our local maximum is going to be the point 1.39, 0.42. And our local minimum is negative 72 hundredths, comma, negative 4 and 27 hundredths. For the second example here, your intercepts are going to be 1, 0 and 2.380. Notice I'm giving 2 decimal places for each of these. Your local maximum is 0.4, and your local minimum as 1.8, comma, negative 4.3. And that should be a comma. It won't let me give a comma between them. So try them on your graphing calculator. If you can't find them, don't get frustrated. We will talk about those two some more in class tomorrow and exactly how to do it on your calculator. I'll put the calculator up on the board and go through it with you. Let's look at this last column. It's using direct substitution versus using synthetic substitution. So we want to look at the difference between the two. So for example 1, if I use direct substitution right here, I'm just going to take negative 2 and put it in for all the x's. So I'm going to say f of negative 2 equals negative 2 with parentheses to the 4th power plus 2 times negative 2 with parentheses to the 3rd power plus 3 times, again, negative 2 with parentheses to the 2nd power minus 7. And if you put that all into your calculator, you'll find that f of negative 2 equals 5. So this is direct substitution is something we've done before. We've plugged our numbers in for our variable and simplified, and that's really what we're doing here. So for the second example, if I want to find f of negative 3, I'm going to put negative 3 in here for x. So we want to find x, what our function is when x equals negative 3. So I plugged negative 3 in for x there. And plug negative 3 in again with parentheses to the 4th power. Minus 6 times negative 3 to the 2nd power. Plus 3 times negative 3 squared. Minus 7 times negative 3 minus 5. And if you put that all into your calculator, you'll get f of negative 3 equals 529. Don't try and simplify that piece by piece. Just put it all into your calculator at once. I tend to see mistakes when students try and do that one piece at a time. So just put it all right into your calculator and you should get 529. So the next method that I'm going to show you is called synthetic substitution, and this is like our synthetic division. So if I want to find my value for f of x when x equals 2, so really I'm finding f of 2 here, but I'm going to write it a little bit differently. So I'm going to do it just like I did synthetic division. I'm going to put my 2 on the outside. Then I'm going to fill in my coefficients, 5, 3, negative 1, 7. I'm going to drop my 5 down. 2 times 5 is 10. 3 plus 10 is 13. 2 times 13 is 26. Negative 1 plus 26 is 25. 2 times 25 is 50. 7 plus 50 is 57. This value right here, our remainder, actually tells us what f of 2 is. So f of 2 equals 57. So it's kind of a neat little nifty trick here. Instead of doing our direct substitution, we can use synthetic substitution to find the values at given x values. So the next one, I suggest you pause it and try this one on your own. But really, we're looking for g of negative 1 here. So pause it, write it out. Okay, so you should say negative 1. That's what goes on the outside. My first coefficient is negative 2. My second is negative 1. There is no x squared term, so I've got to put a 0 in to hold the spot. My third value is 4, and my last is negative 5. So again, this first one's going to drop right down, negative 2. Negative 1 times negative 2 is 2. Negative 1 plus 2 is 1. Negative 1 times 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is 1. 4 plus 1 is 5. Negative 1 times 5 is negative 5. Negative 5 plus negative 5 is negative 10. So here's my remainder. So I know that g of negative 1 equals negative 10. So again, a neat little trick there. Instead of plugging everything into our calculator, we can just use synthetic division. Okay, let's look at the back side of your frame. Okay, so section 5.2 and 5.8, again, we're looking at end behavior this time for our polynomials. So this frame is about describing the end behavior without graphing. So it's about describing the end behavior of graphs without graphing. So we have two types of functions here. Functions called odd functions and functions called even functions. So it's called an odd function if our degree of the polynomial is an odd number. It's called an even function, then, if the degree of polynomial is an even number. Makes sense. If the degree is odd, it's called an odd function. If the degree is even, it's called an even function. So for odd functions, we have two different types that we could look at. First one, our leading, I should say leading coefficient. If our leading coefficient is a positive number. So if I had like 6x to the third, okay, x to the third, 3 is an odd number, so it's an odd function. Our leading coefficient is 6, so that's a positive number. We could also have our leading coefficient. I should put 2f's, coefficient has 2f's, equals a negative number. So you could have your leading coefficient be a positive number or a leading coefficient be a negative number. So this is the difference that we're looking for in odd functions. So what you need to know is that as x goes to negative infinity, so what that means, if I draw my coordinate plane here, x going to negative infinity means my x value is coming this way. So as x goes this way, my function, f of x, also goes to negative infinity. So as I move in this direction, my function comes downward. So my function is going to look something like this. And then on the other side of the graph, so that's one side, one end behavior. On the other side of my graph, as x goes to positive infinity, then the function f of x is going to go to positive infinity as well. So as x goes this way, then my function is also going to go up this way. So that's my end behavior on both sides. And my graph in the middle will change a little bit, but it's going to look something like this. So let's look at if our leading coefficient is negative. So if we have an odd function, so our degree is an odd number, if our leading coefficient is negative, what we see is that as x goes to negative infinity, then our function, f of x, goes to positive infinity. So on my graph, as x goes to negative infinity, my function goes to positive infinity. So it looks something like this. And then on the other end of the graph, as x goes to positive infinity, f of x, my function, is going to go to negative infinity. So as my x increases, my function is going to go downward like this. So my end behavior over here is going to look like this. And in the middle, it's going to look something like that. That middle shape is what's going to change, but we're looking at our end behavior of our graphs here. So now let's look at even functions. So again, we're going to talk about our leading coefficient being positive versus negative. So our first one, if our leading coefficient equals a positive number. And on the bottom here, we're going to say if our leading coefficient equals a negative number. So let's look at the top one first. So if our leading coefficient is a positive number, then what we know is that as x goes to negative infinity, so as x gets smaller, then our function f of x goes to positive infinity. So if my graph looks like this, here's my coordinate plane. So the end is going to look something like this on the left side if our degree is even. So we have an even function, we have a leading coefficient that's positive. On the other end of this graph, as x goes to infinity, then f of x goes to infinity as well. So if we have an even function both ends of it go to positive infinity. And then the middle of it looks something like this. But both ends go to positive infinity. And if you notice, these graphs kind of flipped, didn't they? This graph's going to do the exact same thing. It's actually going to flip upside down if my leading coefficient is a negative number. So my graph is going to look something like this if my leading coefficient is a negative number. So what that tells us is that as x goes to negative infinity again, because my x is decreasing, then my function is also going to go to negative infinity. On the other side of this one, as x goes to positive infinity, then my function, f of x, is going to go to negative infinity. So for even functions, both ends of the graphs kind of go either both up or both down. It depends on whether it's a positive or a negative coefficient. So what's important to know about this, what's the so what down here, is you should be able to describe the ends of your graphs. Without even graphing them, you should be able to look at them, look at your leading coefficient, and whether it's an odd or even function, and describe what the graph is going to look like. So this is the end of this lesson. Please make sure if there's any questions, you star them so we can talk about tomorrow. Have a great day.